Hey guys, welcome to lesson 2.3, where we discuss correlation, strength, and direction. So we talked about the strength and direction of a linear relationship. Here we have positive direction, meaning that as one variable height increases, the other one is expected to increase as well, in this case, handspan. Here we have an example of a negative direction. As mileage on a car increases, the resale value tends to decrease. So positive means as one goes up, we expect the other one to go up as well. Negative means as one goes up, we expect the other one to go down. Now, strength just means, on average, how close are the points to the line of best fit. So this would be a stronger relationship because, on average, these points are closer to the line than the points over here. What does correlation tell us? So the correlation between two quantitative variables, it has to be two quantitative variables. So two variables where we can find the average, things that you can't find the correlation between categorical variables. So things like eye color, etc., you can't correlate them. There's association, but not a correlation. It's a number that indicates the strength and direction of a straight line relationship. So a correlation coefficient tells us two things, strength and direction. The strength of a relationship is determined by the average closeness of the points to a straight line. The direction is determined whether one variable generally increases or decreases as the other one increases. So again, strength of a linear relationship, this is a stronger relationship than the one on the right, stronger than the one on the left. Correlation coefficients are always values between and including -1 and 1. -1 is a perfectly strong negative correlation. +1 is a perfectly strong positive correlation. So the magnitude of the correlation indicates the strength of the relationship. Magnitude being the absolute value. Indicates the strength of the relationship, which is the overall closeness of the points to the straight line. The sign of the correlation just tells you the direction of the relationship. So negative means it's a negative relationship. Positive means it's a positive relationship. Correlation of either -1 or 1 indicates that there's a perfect linear relationship. Basically, none of the data points deviate from the straight line. They're all perfectly on the straight line. Visualizing values for a correlation coefficient. This is not like exactly -1. I know it says that, but this is like super close to -1. This is super close to +1. This is a strong positive correlation, strong negative correlation, and this is a correlation of 0. Here's an example. Figure below displays for a sample of 116 students and the relationship between the reported hours of sleep during the previous 24 hours and the reported hours of study during the same period. All right, so this is a correlation coefficient of -0.36. You can see a reasonable negative relationship. As study hours increased, we expected the hours of sleep to decrease. 3 important caveats. Each of the following actions will cause misleading regression and correlation results. Extrapolation. Extrapolation means going way outside of the range of x values, allowing outliers to overly influence the results, and using correlation and straight line equations to describe curvilinear data. So extrapolation, it's risky to use a regression equation to predict values outside of the range of observed data, a process called extrapolation. It's quite acceptable to use a regression equation for interpolation, which is estimating y values within the range of data. So for example, we have this relationship between thousands of miles driven and resale value of a car. So if I use this to try to get a resale value of a car that has 200,000 miles on it, I'm probably going to get a negative value, which is not going to make sense. This is because I'm extrapolating. I'm going way outside of the range of the data. Here, the range of the data, goes a little bit over 100,000 to a little bit over 10,000. So if I try to find the resale value of a car with, let's say, 70,000 miles on it, that's going to be interpolation, and that's going to be okay. But for 250,000 miles on it, it's going to be extrapolation, and that's not going to give me reliable results. Outliers with extreme X values can have a lot of influence, and depending on where those points line up, they can either deflate or inflate a correlation. So here's data for major earthquakes between 1850 and 2019. And you have one value, which is the 1906 San Francisco earthquake, that when you include this with the rest of the data values, you have a positive correlation. But so a correlation coefficient of 0.253, so a weak positive correlation. But when you remove that one outlier, you have the rest of the data has a much stronger negative correlation. So one extreme outlier can have a significant effect on the overall correlation of the data. So it said the San Francisco earthquake in 1906 occurred before earthquakes building codes were enforced. Many of the largest earthquakes occurred in very sparsely populated areas. So in general, this data is not great for analysis. In terms of like, there's not a clear relationship between these variables, but especially when you include that outlier, you kind of throw the results out the window. All right, lastly, the last example is you've got table below lists the population of the United States for each census between 1790 and 2010. And the data is growing at a exponential rate. So if you try to fit a line to an exponential growth, and then you start making predictions kind of out into the future, they become increasingly inaccurate. So you want to make sure that you want to use the right model to fit the right data. If for whatever reason your data is curvilinear and you start using a line to try to fit it, you're going to run into issues.